start. 3, 2, 1. We have ignition and liftoff of Discovery.
At the moment of launch, it's like a giant picks up the shuttle and just sort of lurches it forward. And you really feel that, a tremendous acceleration. And that was the most exciting part of the whole launch for me.
Houston's now controlling. Roll maneuver is underway.
When I was in grade 3, I was in my classroom listening to the voice of John Glenn, the first American astronaut to do an orbit around the Earth. And it was on that day when I decided that I wanted to become an astronaut, and when I learned what space was all about for the first time.
Velocity 1,000 feet per second, altitude 200,000 feet.
Discovery, go at throttle up.
Maneuver is underway.
Roger, go at throttle up.
Have you ever wondered what it would be like to travel through the solar system? What would you need to take with you? How long could you survive? We journey through space every day on a ship called Earth. What makes life possible on our spacecraft? It's the interaction between the energy of the sun and the components of our thin layer of existence, the biosphere.
The sun is so far away, you'd think most of its energy would be lost before it reached Earth.
Sunlight travels nearly 150 million kilometers on its journey to Earth. Although only 1/2 billionth of the energy the sun gives off reaches us, it's more than enough to sustain life. Everywhere you look, the Earth's living and non-living systems are using the sun's immense energy. Plants, animals, air, water, even the land absorbs energy. How is energy from the sun captured or absorbed on our planet?
Hey.
Hey, ready to go?
Yeah.
How is solar energy stored?
Looks like it's going to be a good day today.
Oh, it's gorgeous out.
And how is it used? The flow of solar energy through our biosphere is simply science. Our spaceship, Earth, acts as an open system with energy from the sun entering and leaving it every second. This huge ecosystem called the biosphere consists of Earth's land, air, and water. Life on our planet exists only within the biosphere and requires a constant supply of energy, for the most part, solar energy. Although the biosphere has a large surface area, it's only about 15 kilometers deep at its thickest point. The biosphere extends from the tops of mountains down into the deepest caves. It includes the soil, all surface waters, and the oceans.
"30 minutes after launch, for the first time, I looked out the window there and saw Earth. To me, it really looked like a spaceship Earth, you know. I was in a spaceship called the Space Shuttle Columbia, but looking at this orb just floating in space. It very much had its own self-contained life support system. It had water there. It had an atmosphere there. But it looked vulnerable because the atmosphere is very, very thin.
Hey, how's it going?
Great.
Excellent.
Let me give you a hand. You know, it's a good thing we aren't going up into space. We'd be pretty ill-equipped.
That's for sure.
What would you take for survival?
I don't know. CDs, video games, a double cheese pizza.
You might want to leave room for something like, I don't know, oxygen?
Yeah, that might come in handy.
Aboard the space shuttle, we have what we call an open-loop life support system. So we're not able to recycle all the gases that we generate or the wastewater that we generate as well. Instead, we bring along our own oxygen with us, and then we have to remove carbon dioxide from the air because, as you know, we expire carbon dioxide into the air. We get our power not from solar arrays or from nuclear power reactors, but from something called fuel cells. That is, we fly tanks of liquid oxygen and liquid hydrogen. And when you combine oxygen and hydrogen together, you get two things. One, you get water. And number two, you get electricity. So we use electricity to power all our systems inside the shuttle, and then the water that we generated we used for drinking.
Sounds like your CDs and video games wouldn't cut it up there.
Yeah, I think I'll have to pack lighter.
I think you're a spaceship Earth kind of guy.
The sun's energy reaches the upper surface of the biosphere at an average rate of 1,360 watts per square meter. This means each square meter receives enough solar energy to light almost 14 100-watt light bulbs. That's a lot of power. The total solar energy that reaches the upper atmosphere in a year is greater than the energy of an atomic bomb.
I guess the main thing that I noticed when I turned my view away from Earth and out into space was that the stars and the moon and obviously the sun seemed a lot brighter from my vantage point in space than it did on Earth. And of course it makes sense because there's no intervening atmosphere between my eyeball and these celestial objects. Also, of course, stars don't twinkle in space for the same reason. There's no intervening atmosphere there. So you look at the stars and you see one single bright spot.
Our planet not only receives solar energy, it also releases it. There's a balance between a total amount of energy the Earth absorbs and gives off to outer space.
What if the balance weren't maintained?
If Earth only absorbed energy, it would become unbearably hot.
Like Mercury.
And if our planet only released energy?
Well, then it would be too cold for life to exist.
The steady state, or balance, is called the heat budget. It's maintained by the components of the biosphere interacting with the solar energy they receive. What are the components of the biosphere?
Well, Sarah said that the biosphere goes as high as the mountaintops, so I guess that includes the air.
Well, the atmosphere, actually. All life depends on this thin layer of gases which surrounds Earth. It allows light rays to pass through, protects us from extreme temperature changes, and causes most meteorites entering to burn to dust. What's another component of the biosphere?
Water. You know, lakes, rivers, oceans.
It's called the hydrosphere, and it includes all bodies of water, surface water in ocean depths, as well as water in the air and ground. Water is always cycling in and out of our atmosphere. It evaporates, rises and condenses into clouds, and falls as rain and snow, forming streams, lakes, and rivers.
And that cycling causes weather.
It's an important element of climate. So what's the third component?
The soil, where roots and microorganisms exist.
We refer to the rigid outer crust of rock on Earth as the lithosphere. It's about 80 kilometers thick. Over millions of years, our planet's rocky surface has eroded. Crumbled rock, combined with decomposed plant and animal material, formed soil.
So the biosphere.
Consists of the atmosphere, hydrosphere, and lithosphere.
Right. It balances the sun's energy on Earth and provides for the conditions of life.
Hey, where am I? So Darren, if energy is always moving through the biosphere, can some of it get destroyed?
I say no. It just changes.
That's right. Energy can never be created or destroyed, only converted from one form to another. And just like matter, it's always changing form.
What do you consider matter?
Well, anything that has mass, right?
And occupies space. Matter can include things that we can't see, like gases.
So our spaceship, Earth, has a way of using the sun's energy.
And it converts energy and matter so we can survive the trip through space.
Right. The sun's energy is absorbed and converted into many different forms. And energy is the ability to do work. So how do we know if something has energy?
You can see the evidence of energy when work is done.
Right. The addition or removal of energy can cause changes in matter which you can observe.
So when energy changes, so does matter.
Energy can change the physical and chemical properties of matter.
Physical properties, that's what we can see, right? Like this log. We can see that it's solid, brown, and rough.
Physical properties are the things we can sense. They describe what something's like.
What about chemical properties?
Well, they can't be described until a substance undergoes a chemical reaction. They describe how one substance reacts with others.
So the chemical properties of this log describe how it reacts with the oxygen in the air when it burns.
Watch this mini movie of Tanya and Devender's activities. See if you can find any signs that energy was converted. Here's a hint. Look for any changes in matter. How did you do? Well, let's take another look. And remember, changes to matter are signs that energy is present.
Energy was converted when the log was placed in the fire. It burnt to ashes.
So a change in energy caused a change to the log.
The outside of the marshmallow turned brown and became crisp, and the inside gooey.
An increase in temperature changed the marshmallow's properties.
My wet towel dried in the hot sun.
Energy caused the liquid to become vapor.
What about the camera?
The camera used light energy to create images on the film.
Our chocolate bar melted when it was left out in the hot sun.
Again, an increase in temperature altered the properties of the chocolate bar. In all of these examples, a physical or chemical change indicated the transfer or conversion of energy. So how did the energy affect your marshmallows?
Well, the marshmallow gained energy from the fire, which caused it to start to change from a solid to a liquid.
Since energy is the ability to do work, when matter changes, we know work has been done.
If work's been done, there's been a change in energy.
Throughout our biosphere, many processes capture, convert, and distribute energy from the sun. One is photosynthesis, which most plants use to absorb, convert, and store light energy. This process enables them to live. The products of photosynthesis allow people and animals to exist. In a similar chemical reaction, light energy is used to create images on film. And sometimes, just by focusing energy, you can control it. These processes are part of an open system, Earth, that relies on energy from the sun.
People who build solar houses have borrowed this idea. They use systems of capturing, converting, and distributing light energy to run the home.
This house has 3 main systems for absorbing solar energy. A central fireplace,
Which burns wood, a renewable resource.
a concrete slab under here, and solar electric panels on the roof and on the southern wall of the house.
The fireplace and the concrete slab absorb the solar energy that comes through this south-facing window.
This energy is changed to thermal energy of the air, which heats the rooms on both floors.
The energy trapped in the fireplace is also used, along with the energy captured by the solar collection system to heat the water for the hot water storage tank.
Even the heat from the water is recaptured. As warm water from the bathtub goes down the drain through a pipe, the heat is transferred to water coming up through a smaller pipe.
Homes like this make a lot of sense. Renewable resources are used to operate the house, so owners don't have to pay big utility bills.
Solar homes are the wave of the future, yet they use processes that have been in existence since the beginning of time on Earth.
Right. Processes that use the energy of the sun by harnessing it in a number of different ways.
Light energy can cause changes in matter. Photosynthesis is an example of an energy conversion in a living organism. We can often see energy at work because of the physical changes it causes. But how do we know if a chemical change has occurred? For example, how can we show that a chemical reaction has occurred in photosynthesis? In a chemical reaction, matter changes to produce a new substance with properties different from those of the original. So what's our next step?
If photosynthesis is a chemical reaction caused by light, we predict we'll find different substances in a leaf that's been exposed to light,
rather than one that's been deprived of light. This geranium has been in a dark cupboard for the past few days.
We're going to cover one of the leaves with a piece of aluminum foil. As you can see, we cut a small square in the foil to allow light to reach the top of the leaf.
Now, we'll place a geranium in a bright light for the next 24 hours.
Do you think we'll find a difference in the leaf? During photosynthesis, plants produce glucose. Some of the glucose is stored as starch. We can test for this substance using iodine. A blue-black color indicates the presence of starch.
The geranium has been exposed to bright light for 24 hours now. To prepare our leaf for the starch test, we put it in boiling water.
When the leaf becomes limp, we transfer it to another beaker half full of ethanol.
We set the smaller beaker into this one to warm the ethanol.
Then we wait 5 minutes and see what happens. Now the leaf is a pale yellow color. It looks like the ethanol removed the green.
I'll record this observation.
We remove the leaf and place it into a beaker of cold water.
Next, we spread the leaf right side up in a petri dish. And then place it on a piece of whiteboard.
We flood the leaf with an iodine solution and observe for several minutes. The small square, the part of the leaf that was exposed to the light, turned black from the iodine solution,
while the part of the leaf that wasn't exposed still remained yellow.
So what do your observations tell you?
We see that the part of the leaf exposed to light contains starch. The part of the leaf shielded from the light doesn't.
So our prediction is right. Light is required for photosynthesis.
Good. Plants, which belong to a group of organisms called producers, convert light energy into stored chemical energy during photosynthesis. In fact, chemical changes in photosynthesis and many other processes cannot occur without light energy.
The sun's energy causes chemical reactions in processes like photosynthesis. But did you know solar energy is also the energy source for winds? Our atmosphere is a complex weather machine with moving parts fueled by the energy of the sun. Sunlight warms our biosphere, causing water to evaporate and air to move. This movement of air drives our weather and is a major factor affecting temperature, precipitation, winds, humidity, clouds, storms, and air pressure. Have you ever watched a hot air balloon float? The balloon is equipped with a heater which warms the air inside the balloon. When this air is heated, it expands, becoming less dense than the cooler air surrounding the balloon. This makes the balloon rise. The same principle applies in our biosphere. The warming of the lower atmosphere causes the air to expand and rise, replacing the cooler air. This is called convection. Convection moves thermal energy in gases and liquids. Convection explains why winds occur where large bodies of water and land meet. When the sun shines, the air above the land warms up faster than the air above the water. This is due to the fact that the land's heat capacity is lower than that of the water.
Warm air rises, so
if the air above the land rises, it must be replaced by some other air.
the cooler air blowing in from the water.
This is called a convection current.
When the sun goes down, does the opposite happen?
Exactly. At night, the land and the air above it is cooler than the water and the air above it. This creates a convection current, flowing from the land out over the water.
60 seconds of science.
Seeing is believing, right? Let's create a convection current that we can actually look at. We take an aquarium and fill it with water. Then we'll add some ice cubes to one end. About half a dozen or so should be enough for this size of aquarium. Next, we'll add some potassium permanganate crystals to the end where the ice cubes are. As the crystals dissolve, the solution indicates that the water is flowing. A convection current is created when the cold water at this end sinks and the warm water here moves in to replace it. You can see that the current circulates in this direction. It's even strong enough to hold the ice cubes at this end of the aquarium. Keep in mind that convection currents can occur in air as well as in water. A convection current. You saw it here on 60 Seconds of Science.
Some solar houses also use convection currents as a way of heating rooms.
Warm air rises to the second floor, where the doors and loft-like openings allow it to circulate.
Yo, let's rap.
In some ways, we're all astronauts traveling on a spaceship called Earth. Our craft support system is the Biosphere, which is fueled by the sun. The components of our engine captured this energy and convert it into usable forms. The flow of solar energy through the Biosphere sustains life and is simply science.
When I look back at Earth, even though I was in relatively low orbit, I could see that it was a round planet floating in the middle of nothingness. And it was a very beautiful planet. It had wonderful shades of green and blue in the oceans and even yellows in the desert areas. But very much I felt like we were vulnerable living on Earth. It's very much a spaceship moving through Earth with a very fragile environmental control system. The atmosphere around the Earth is very delicate, thin like a veil. So I got the impression that, number one, we're very vulnerable on this spaceship Earth, and number two, we have to do a little better job of taking care of our life support system.